Good afternoon, everyone. I will present my work entitled Integration of UAV-based photogrammetric point cloud on hyperspectral data for tree species classification. This work was a part of my PhD study at the National Institute for Space Research, and it was made in partnership with Fundación Edmund Mar, Santa Catarina State University, and São Paulo State University. I will start with a brief introduction about the subject. For tree species mapping, usually field surveys are efficient. However, they tend to be time-consuming and costly to be executed in a large scale and in a systematic way. And this restraint has fostered the use of remote sensing as an effective means for tree species mapping. However, even the use of remote sensing faces some challenges to map tropical tree species due to some challenges of these environments, like the higher number of tree species with similar spectral response, multiple strata, similar overlapping and interconnected canopy, which difficult to identify the borders of the individuals, crowns with irregular shapes and size, and the presence of dominant and minority classes, which result in an imbalanced sample set that must be considered during the classification process. Fortunately, some of these problems could be minimized thanks to the improvement of the remote sensors over the last decades that enables the identification of individual trees even in a dense canopy. And recently, the small format camera on board of UAV allows to acquire images with both high spatial and high spectral resolution, and starts to be used for tree species classification. And also, besides the high spectral and spatial resolution, small format cameras allow the extraction of three-dimensional information from a photogrammetric point cloud using an image spectroscopy. And also this information can be valuable for tree species classification because it allows to extract parameters like the vertical structure among the species. Besides the data, also the choice of the classifier is important for tree species mapping, and in this regard, many studies demonstrate that machine learning are efficient, more efficient than the parametric algorithms when the feature space is complex, and with the data set present with statistical distribution. So the goal of this work was to test the integration of UAV-hyperspectral images and UAV-photogrammetric point cloud for the classification of 14 tree species in a subtropical forest area using machine learning classifier. This work stands out because we try to classify a higher number of tree species, because usually in tropical forests the studies are restricted to classify 3 to 8 species because of this challenge of these environments, and also because it was one of the first work testing the integration of the photogrammetric point cloud for a tropical forest. The study area is located in south of Brazil, in Santa Catarina State. It's close to Paraná State, where we are now, and it belongs to the Atlantic rainforest biome and the Mixed Ombrophilous Forest phytophysiognomy, which means that the area contains both broadleaves and coniferous tree species, and it's a very high diversity area. The area has approximately 30 hectares. The material and methods, so we'll be brief here in this workflow. The UAV-hyperspectral images and the photogrammetric point cloud were pre-processing. In the field work, we identified and geolocated the tree species. That after that, we manually delineate the individual tree crowns over the images, and the crowns were split in training and test set for the classification. We compose the data sets, one data set only using the hyperspectral images, and the other data sets combining the hyperspectral images with the photogrammetric point cloud, some elevation features, and also with the canopy height model. Then we perform the classification and the accuracy assessment, and we generate the thematic maps. The hyperspectral data were acquired with a camera based on Fabry-Perot Interferometer. This camera has two CMOS sensors that capture data from the range of 500 to 900 nanometers. It allows to capture until 25 spectral bands that are flexible configured. Some information here about the flight. The final spatial resolution was 11 centimeters, and the images were acquired with a great overlap, which enabled the creation of a photogrammetric point cloud with 35 points per square meter. We also use some LiDAR data only to compute the digital terrain model and to allow us to compute the canopy height model. The digital surface model and the elevation metrics were extracted from the photogrammetric point cloud. The results show the incorporation of the elevation features and the canopy height model lead to an increase of 10% in overall accuracy when comparing with the use only with the VNIR dataset alone. The incorporation only of the canopy height model lead to an increase of accuracy in 5%, and the incorporation of only the elevation features, that the increase in accuracy was almost 9%, which means that even when lacking some LiDAR data to compute the canopy height model, with elevation metrics brought us a great increase in accuracy. These box plots show the distribution of the elevation features and the canopy height model values of each three species. It can be noticed that in the canopy height model, some species have similar values, and here in the elevation features, the species are more discernible. And for this reason, these elevation metrics were more useful, for in this case, than the canopy height model. This is a thematic map, considering only the sample's location. We did not extrapolate the classification of the entire area because not all the species were considered here. So it can be noticed that in general the classifier identified correctly labeled the three species. However, some cases, as we can see here, not all the pixels inside the individual tree crown were correctly labeled. It can be occurred due to the higher resolution of these images that led to a more variability inside the individual tree crowns, and this problem could be minimized using an object-based classification. So the conclusion was that the inclusion of the elevation features from the photogrammetric point cloud and the canopy height model increased accuracy in 10%, only the elevation features in 9%, and this result could be useful not only to classify a large number of tree species, but also if you want to focus on only the endangered ones, like in this case the Araucaria and Segrella species. And like our current work, this research has advanced in the last months, and we already tested the object-based classification and the majority vote in which the pixel classification was aggregated into segments, and this we observe an increase in 5% when considering the machine learning classifiers. We also tested a convolutional neural network. In this case, the increase was 22% more accurate than the machine learning when only considering the hyperspectral bands. And for future work, we are exploring the potential of the photogrammetric point cloud for individual tree crown delineation, and also some methods involving the extraction of deep features from the photogrammetric point cloud and using the convolutional neural network classifier. And this is the reference, and this paper contains more information about this research. And thank you very much.